Hello everyone, today in this class we will continue to learn logarithmic operations. Firstly, please recall the arithmetic properties of logarithms learned in the previous class. If a is greater than 0 and not equal to 1, m is greater than 0, and n is greater than 0, then with a as the base. The logarithm of m multiplied by n is equal to the logarithm of m with a as the base plus the logarithm of n with a as the base. The logarithm of m with a as the base n is equal to the logarithm of m with a as the base minus the logarithm of n with a as the base. The logarithm of a as the base m to the power n is equal to n times the logarithm of a as the base m. Okay, let's take a look back at these three computational properties as a whole. In the first property, can we only ensure that m multiplied by n is greater than 0? M multiplied by n greater than 0 includes two situations: m greater than 0 and greater than 0, and m less than 0, while n is also less than 0. When both m and n are less than 0, we cannot guarantee that these two logarithms are meaningful. That is to say, in this formula, we must ensure that any number appearing in the true position is a positive number and that the logarithm is meaningful. In the second property, the ratio of m to n is greater than 0. Is it sufficient to only ensure that m is greater than n by 0? Similarly, there is a possibility that both m and n are negative at the same time. If both m and n are negative at the same time, then the values of these two logarithms will also be meaningless. Therefore, all logarithms that appear in the equation must ensure that their true numbers are greater than 0. Similarly, the nth power of m in the third point is also the same, and it is not enough to only ensure that it is greater than 0. We also need to ensure that the m appearing here, that is, the number at the position of the true number, is greater than 0. Secondly, from the perspective of computation, the operations on the left side of the equation include multiplication, division, and power multiplication. On the right-hand side of the equation, we actually performed addition, subtraction, and multiplication operations. Therefore, in terms of the level of computation, we have lowered the level of computation, thereby simplifying the operation. In the history of mathematics, people have made great efforts to create commonly used logarithmic tables and natural logarithmic tables. We can find the constant logarithm or natural logarithm of any positive number by searching. Now, we can use calculation tools to find the common logarithm or natural logarithm of any positive number. How to calculate such a logarithmic value if the base is not 10 or e? That is to say, can we convert it into a logarithm based on 10 or e? Okay, let's start today's learning. Firstly, let's take a look at exploration 1. Please use a computational tool to find the approximate values of ln 2 and ln 3. Okay, according to the definition of logarithm, can you use the values of these two numbers you just obtained to find the value of the logarithm with 2 as the base and 3? Okay, here we need to convert the logarithm with 2 as the base 3 into ln 2 and ln 3. We found that in ln 3 and the logarithm with 2 as the base 3 is in the position of the true number. Therefore, I think if we can separate 3, we can perform a base swapping. So, how can we separate 3? Okay, we can proceed based on the definition of logarithm. Firstly, we set 2 as the base and the logarithm of 3 is equal to x. According to the definition of logarithm, we can obtain that the x square of 2 is equal to 3. In this way, 3 will be separated. Since the x square of 2 and the value of 3 are the same, they both take logarithmic values with e as the base, and the values are still the same. Therefore, we simultaneously take the logarithm with e as the base on both sides and obtain that the x square of ln 2 is equal to ln 3. According to the properties of logarithmic operations, obtaining x times the value of ln 2 equals ln 3. Therefore, we can calculate x, which is the logarithm of 2 to 3 that we want to represent, so that it is equal to ln 3 to ln 2. According to exploration 1, the values of the two numbers we obtained are approximately equal to 1.585 when substituted in. We have found that we have transformed logarithmic values based on 2 and 3 into logarithmic values based on e. So can we move it in a way? Can we represent the logarithm of a as the base b by comparing the logarithm of a with the logarithm of b with c as the base? Among them, a is greater than 0 and not equal to 1, b is greater than 0, and c is greater than 0 and not equal to 1. We can analogize the process just now. Firstly, we also set a as the base and the logarithm of b is equal to x, thus separating b and obtaining that a's x side is equal to b. We take the logarithm of c as the base on both sides, so the logarithm of a's x side with c as the base is equal to the logarithm of b's x side with c as the base. That is to say, x times the logarithm of a with c as the base is equal to the logarithm of b with c as the base. This way, we can convert the logarithm of a with b as the base to the logarithm of c with a as the base. This is the base-changing formula we are going to learn today. We can see that the conversion formula converts the logarithmic value of a as the base b into the quotient of two logarithmic values on a year-on-year basis. Molecules are logarithms of true numbers. The denominator is the logarithm that takes the base of the original logarithm as the true number, so that we can achieve the purpose of changing the base. This formula can also be applied, which means that the quotient of two identical logarithms can be converted into one logarithm. The base of this new logarithm is the true number of the logarithm of the denominator in the fraction. The true number of the new logarithm is the true number of the logarithm in the molecule. So we can achieve the goal of simplification. Okay, now we can use the transformation formula to directly convert the logarithm with 2 as the base 3 using ln 2 and ln 3. Okay, with 2 as the base and 3 as the logarithm, we can immediately write it in the form of ln 3 to ln 2. So we can also use log 2 and log 3 to represent the logarithm with 2 as the base 3. Utilize the bottom changing formula. Convert the logarithm of 2 and 3 to 2 base 10 logarithms, where the true number in the numerator is the original true number, and the true number in the denominator is the base of the original logarithm. Okay, we have learned the bottom changing formula. Now let's test if we have mastered it. Let's take a look at application example 1. Evaluate using 2 as the base 3 logarithm, multiply by 3 as the base 4 logarithm, multiply by 4 as the base 5 logarithm, and multiply by 5 as the base 2 logarithm. This is the form of multiplying for logarithms, and the bases of these for logarithms are not the same. We do not have corresponding computational properties to solve this problem, so we can use the base replacement formula to convert it. Who should we use as the base instead? In fact, any number greater than 0 and not equal to 1 can be used as the base. For the convenience of writing, I switched to a base of 10. In this way, a logarithm of 2 to 3 is converted to log 3 to log 2, and a multiple of 3 to 4 is converted to log 4 to log 3. The logarithm with a base of 4 to 5 is converted to log 5 to log 4, and the logarithm with a base of 5 to 2 is converted to log 2 to log 5. The final result is equal to 1. Through this question, please guess, what is the value of multiplying the logarithm of base a by the logarithm of base b by the logarithm of base c by the logarithm of base a? How to verify it? I hope everyone can verify after class. Can you draw any other conclusions from this question? Please also complete it outside of class. Okay, let's take a look at application 2 again. In question 1 of 4.2.1, we obtained the x squared relationship where y equals 1.11 through exponentiation. That is to say, after x years, the number of tourists to scenic area B is y times that of 2001. So, if we want to calculate how many years have passed since the number of tourists to scenic area B doubled compared to 2001, how should we calculate it? To calculate this problem, one is actually looking for the value of x. According to this relationship, we can actually convert x to the logarithm of y with 1.11 as the base, where y has a value of 2. Therefore, x is equal to the logarithm of y with 1.11 as the base. We will perform a bottom shift again, with 10 as the base and log 2 or above as log 1.11. By looking up the table, we can obtain this value, which is approximately 6.64 and 7 o'clock. From this, it can be concluded that after approximately 7 years, the number of tourists to scenic area B can double that of 2001. Okay, let's take another look at the question. Although humans are currently unable to accurately predict earthquakes, scientists have gained some understanding of earthquakes through research. For example, the unit of energy E released during an earthquake is joules, and the relationship between log E and the Richter magnitude M of the earthquake is 4.8 plus 1.5 times M. March 11, 2011. A magnitude 9.0 earthquake occurred in the northeastern waters of Japan. How many times the energy released was that of the 8.0 magnitude earthquake that occurred in Wenchuan, China on May 12, 2008? Please be precise to 1. This question is about the relationship between the Richter scale of an earthquake and the energy released during an earthquake. Everyone can guess first. What is the energy released by an earthquake with a difference of 1 magnitude on the Richter scale? After we calculate later, we will verify whether our classmates' guess is correct. Okay, let's study this question. Firstly, we need to determine the answer to this question. What is the object of research solution? How to establish a relationship between this object and known conditions? The known Richter scales of 9 and 8 actually refer to the value of m. What we require is the ratio of the energy E released by 2 earthquakes. How can we calculate this value? We can use the logarithmic operation property to solve it. Let's take a look at the specific process. Firstly, let the energies of earthquakes with Richter scales of 9.0 and 8.0 be E1 and E2, respectively. Given that log E is equal to 4.8 plus 1.5 times m, it can be concluded that log E1 is equal to 4.8 plus 1.5 times 9.0. Log 12 is equal to 4.8 plus 1.5 multiplied by 8.0. So the ratio of log E1 to E2 is equal to log E1 minus log 12. So we substitute the two equations just now, and the final calculation is equal to 1.5. In this way, E1 is equal to 10 to the power of 1.5 compared to E2, and through calculation tools, we can obtain the final result, which is approximately 32. In other words, the magnitude difference between a 9.0 earthquake and an 8.0 earthquake is only 1 magnitude, but the energy released by the former is 32 times that of the latter. Please consider why there is such a significant difference in the energy released from 2 earthquakes when their Richter scales differ by only 1 level. The energy released during an earthquake is a very large number, but after logarithmic calculation, it becomes very small. That is to say, the result of exponentiation is reflected in the exponent. For example, if the exponent of x plus 1 of 10 increases by 1, the result of the operation is actually 10 times the original. Adding x to the power of 2 increases the exponent by 2, resulting in a calculation result that is 100 times the original. So conversely, in logarithmic operations, the true number is 10 times greater than the original, and the logarithmic value is 1 greater than the original. If the number of needles is 100 times the original, the doubling value increases by 2 compared to the original. Therefore, after logarithmic operation, the difference in Richter scale is only 1 level, and the energy released will differ by 32 times. That is to say, the change in exponential growth is very fast. In this budget, the change in logarithmic growth is relatively slow, resulting in such a large gap. Okay, let's summarize the content learned in this class. Firstly, we learned the bottom changing formula. Do you remember what the bottom changing formula is? What tasks can the bottom changing formula help us accomplish? In fact, the base conversion formula can help us convert the logarithms of different bases and connect the two. For example, if we want to convert the logarithm of n with m as the base to the logarithm of a as the base, how should it be represented? I hope everyone can master the bottom changing formula proficiently. Could you please recall the operations you have learned so far? So far, we have learned addition and subtraction, multiplication and division, multiplication and square root, and in high school, we have also learned exponentiation and logarithmic operations. Each operation has its own operational properties. There can also be mutual conversion between operations, and we hope that everyone can flexibly grasp the properties and characteristics of these operations, making our operations more concise.